Hello there, and welcome to Sleepy Answers. Tonight, we're drifting into one of the most beautiful questions ever asked, a question whispered by children and pondered by scientists, a question so simple it almost hides the extraordinary story waiting beneath its surface. Why is the sky blue? As you settle in, I invite you to like and subscribe if you enjoy these peaceful explorations of the world around us. It helps others find their way here, one curious mind at a time. But for now, all you need to do is relax, let your shoulders drop, and allow yourself to drift into this gentle journey through light, atmosphere, and the hidden physics that paints our world. The blue sky stretches above us every clear day, so constant and familiar that we rarely pause to consider it. Yet within that endless blue lies a story of particles impossibly small, of light traveling at speeds beyond comprehension, of waves bouncing and scattering through invisible oceans of air. This is not just a tale of science. It is a story about the way our universe speaks through color, about how the tiniest interactions can create the most magnificent displays, about how everything we see is shaped by forces operating at scales far beyond what our eyes can detect. Tonight, as you rest, we will follow light on its journey from the sun to your eyes. We will shrink ourselves down to witness the invisible ballet performed by molecules of nitrogen and oxygen. We will understand why blue dominates the daytime sky, while reds and oranges claim the hours of dawn and dusk. We will discover that the answer to this childhood question opens doors to understanding not just our world, but other worlds circling distant stars. Let your mind relax as we begin this exploration, because the story of the blue sky is, in many ways, the story of how we came to understand light itself, the question that connects us all. Throughout human history, people have gazed upward and wondered. Ancient civilizations wove myths to explain the dome of heaven stretching overhead. The Egyptians saw the sky as a goddess, her body arched across the earth, studded with stars. The Greeks imagined it as a solid sphere of crystal, perfect and unchanging. For thousands of years, the blue expanse above remained a mystery, wrapped in mythology and philosophical speculation. Beautiful but unexplained. A daily miracle that inspired poetry but defied understanding. Children ask why the sky is blue, with an innocence that cuts straight to the heart of scientific inquiry. They have not yet learned to take the world for granted, have not yet absorbed the habit of seeing without questioning. When a child points upward and asks that question, they are engaging in the same process that drives all scientific discovery. They notice a pattern, they wonder about its cause, and they refuse to accept the answer that things simply are the way they are. This is the spirit that eventually unraveled the mystery of the blue sky, though it took humanity thousands of years to develop the tools and concepts necessary to answer what seems like such a straightforward question. The ancient philosophers tried. Aristotle, whose thoughts shaped Western understanding for nearly 2,000 years, believed that color was a property of the objects themselves, mixed with light in various ways. He thought the blue of the sky might come from the darkness of space, mixing with the light of the sun. A reasonable guess, but one that could not explain why the sky changes a color at sunset. or why it looks different at different times of day. For centuries, this question remained in the realm of casual observation rather than systematic study. Interesting, but not pressing. Beautiful, but not urgent. The breakthrough would require several developments. First, scientists needed to understand that light itself was not a simple substance, but a wave phenomenon, something that could be measured, analyzed, and understood through mathematics. Second, they needed to grasp that air, which seems like nothing at all, is actually composed of discrete particles, molecules so small that trillions of them fit in the space of a single raindrop. Third, they needed the concept that these molecules could interact with light in specific, predictable ways. These insights did not come easily or quickly. They emerged slowly through the work of many minds over many centuries, each contributing a piece to a puzzle whose full picture would not become clear until the late 19th and early 20th centuries. The story of solving this mystery is also a story about the nature of scientific progress itself. It shows us that even the most obvious questions can hide profound complexity, that the answer to what seems simple often requires a sophisticated understanding of multiple domains of knowledge. It demonstrates that science is not just about collecting facts, but about building frameworks that let us see the world in new ways. When we finally understood why the sky is blue, we had not just answered a single question. We had developed a deeper understanding of light, matter, and the way the two interact. Tools that would prove useful for understanding everything from the composition of stars to the behavior of microscopic particles to the fundamental structure of reality itself. As you lie here in the quiet dark, consider for a moment how extraordinary it is that we can answer this question at all. We live on a planet wrapped in a blanket of gas that we move through without thinking, breathing it constantly, depending on it for survival. That this invisible medium can take the white light of the sun and transform it into the blue of the sky reveals something profound about the architecture of nature itself. The world operates according to principles that, once understood, make perfect sense. Yet those principles emerge from interactions so small and fast that they lie entirely beyond our direct perception. The blue sky is a reminder that we live in a universe more intricate and beautiful than our ancestors could have imagined, and that human curiosity, given time and patience, can penetrate even the most stubborn mysteries. Understanding light, the foundation. To understand why the sky appears blue, we must first understand what light actually is. This itself is a story worth telling because light is perhaps the strangest and most fundamental thing in our universe. For most of human history, light seemed simple enough. It was the opposite of darkness, the thing that allowed us to see, the warm radiance streaming from the sun or flickering from a fire. But light, it turns out, is far stranger and more wonderful than anyone imagined. Light is a wave. It ripples through space like a wave moves across water, though it does not require any medium to travel through. This was one of the great conceptual leaps of physics, the realization that light could move through empty vacuum, requiring nothing to support its passage. But calling light a wave immediately raises a question. A wave of what? The answer touches one of the deep mysteries of nature. Light is a wave in the electromagnetic field, a rippling disturbance in an invisible field that permeates all of space. When you see light, what you are really detecting is an oscillation in this field, an undulation that has traveled perhaps millions of miles from its source to reach your eye. These waves have two key properties that matter for our story: wavelength and frequency. Wavelength is the distance from one peak of the wave to the next. Frequency is how many of these peaks pass a given point each second. These two properties are intimately related. Light travels at a constant speed, roughly 186,000 miles per second, so if the wavelength is short, more peaks must pass by each second, meaning the frequency is high. If the wavelength is long, fewer peaks pass by, and the frequency is lower. This inverse relationship between wavelength and frequency is fundamental to understanding color itself. What we call visible light is actually a narrow band within a much broader spectrum of electromagnetic radiation. The electromagnetic spectrum extends from radio waves with wavelengths measured in meters or even kilometers, through microwaves and infrared, into the visible range where wavelengths are measured in billionths of a meter, then continuing through ultraviolet, X-rays, and gamma rays with wavelengths smaller than atoms. Our eyes have evolved to detect only that tiny sliver of this spectrum where wavelengths range from about 400 nanometers to 700 nanometers, a range of less than a single octave in the vast electromagnetic symphony. Within this visible range, different wavelengths produce different sensations of color. The longest visible wavelengths, around 650 to 700 nanometers, we perceive as red. As wavelengths shorten, we perceive orange, then yellow, then green. Shorter still, we move into blue, around 450 to 500 nanometers, and at the very edge of visibility, violet, with wavelengths around 400 nanometers. This relationship between wavelength and color is not arbitrary. It arises from the way our eyes have evolved, with different light-sensitive cells responding most strongly to different wavelengths. But the physics of light itself knows nothing of color. Color is an interpretation our brains create from the wavelength information our eyes deliver. The sun emits light across a broad range of wavelengths. It produces ultraviolet light we cannot see, vast quantities of visible light of all colors, and infrared radiation that we feel as heat but cannot see. When all these visible wavelengths mix together in roughly equal proportions, we perceive white light. This is why sunlight appears white, or perhaps slightly yellowish when we look at it, though we should never look directly at the sun for more than a brief instant. The sun is essentially a white light source, producing a spectrum that spans from deep violet through blue, green, yellow, orange, and into red, all blended together into what appears to our eyes as a single unified whiteness. This presents our first clue to the mystery of the blue sky. If sunlight is white, containing all colors equally, why does the sky appear predominantly blue? Something must be happening to that white light as it travels through the atmosphere, something that separates the colors and sends more blue in our direction than other hues. The mechanism for this separation, this sorting of wavelengths, lies in a phenomenon discovered in the 19th century, one of those beautiful examples where theoretical prediction preceded experimental confirmation, where mathematics revealed a truth about nature before anyone had directly observed it. The key lies in understanding that light, though it can travel through empty space, does interact with matter when it encounters it. When a light wave strikes an atom or molecule, It can set the charged particles within that atom into oscillation. The electrons, which orbit the nucleus, begin to vibrate at the same frequency as the incoming light wave. These oscillating electrons then act like tiny antennas, re-radiating light in various directions. This process is called a scattering, and it is the key to understanding the color of the sky. Meet the atmosphere, Earth's invisible ocean. We live at the bottom of an ocean of air. This is not metaphor, but literal truth. The atmosphere that surrounds our planet is a fluid medium, held to Earth by gravity, with its own currents and tides, its own layers and structures, its own composition and behavior. We move through it constantly, but rarely think about it, breathing it thousands of times each day, depending utterly on its presence for our survival. Understanding this ocean of air is essential to understanding why the sky has the color it does. Because it is the atmosphere itself that transforms white sunlight into blue sky. Earth's atmosphere extends hundreds of miles above the surface, but most of it, about 75% of the total mass, is concentrated in the lowest layer, the troposphere, which extends only about 7 to 10 miles up. This is where weather happens, where clouds form, where we live our lives. The air here is relatively dense compared to the thin wisps that exist higher up. Though even at ground level, air is extraordinarily sparse compared to liquids or solids. A cubic meter of air at sea level contains about 25 million trillion molecules, which sounds like an enormous number, until you realize that a cubic meter of water contains about 34 billion trillion molecules, more than 1,000 times as many. The composition of this atmospheric ocean matters deeply for our story. By volume, Earth's atmosphere is roughly 78% nitrogen, 21% oxygen, and about 1% various other gases including argon, carbon dioxide, water vapor, and trace amounts of many other substances. Nitrogen molecules consist of two nitrogen atoms bonded tightly together, forming a molecule denoted as N2. Oxygen molecules are similarly composed of two oxygen atoms, O2. These diatomic molecules, nitrogen and oxygen together making up more than 99% of the air, are the primary actors in the scattering of sunlight. These molecules are incredibly small. A nitrogen molecule measures about 0.3 of a nanometer across. An oxygen molecule is slightly smaller, about 0.003 of a nanometer in diameter. To put this in perspective, visible light waves have wavelengths ranging from 400 to 700 nanometers, meaning that the molecules in air are between 1,000 and 2,000 times smaller than the wavelengths of visible light. This size relationship is crucial. It means that from the perspective of a light wave, air molecules are tiny obstacles, mere specks in an otherwise empty space. Yet there are so many of them that their collective effect becomes substantial. When sunlight enters Earth's atmosphere, it begins an odyssey through this molecular ocean. At the top of the atmosphere, where the air is thin and space is near, light plunges downward, traveling at its constant cosmic speed of 186,000 miles per second. It encounters the first sparse molecules of the upper atmosphere, then progressively denser layers as it descends. With each encounter, each collision with a nitrogen or oxygen molecule, there is a chance for scattering. The light wave sets the electrons in the molecule vibrating, and those vibrations produce new light waves radiating outward in various directions. This process happens billions upon billions of times for every ray of sunlight that reaches the ground. Light scatters and rescatters, bounces off one molecule and then another, gradually spreading throughout the atmosphere. Some light continues straight down, traveling from the sun to the ground with minimal deflection. Other light scatters sideways or even upward, heading back out toward space or wandering through the atmosphere before eventually either escaping, being absorbed, or finally reaching the ground. The result is that the atmosphere becomes filled with light, not just the direct beam from the sun, but scattered light coming from every direction. Light that has bounced through the molecular ocean and emerged heading in new directions. The atmosphere also contains larger particles beyond individual molecules. There are aerosols, tiny suspended particles of dust, sea salt, pollen, and pollution. There are water droplets that form clouds. There are ice crystals in the high, cold reaches of the troposphere. These larger particles scatter light through different mechanisms than individual molecules do, mechanisms that depend on the relative size of the particle and the wavelength of light. When particles are comparable to or larger than the wavelength of light, the scattering follows different rules that do not favor blue light as strongly. But on a clear day, when the sky is that perfect, unblemished blue, it is primarily the tiny molecules of nitrogen and oxygen that determine the color we see, and it is their interaction with light that creates the phenomenon we are exploring. The atmosphere is not uniform in density. Near the ground, molecules are packed relatively closely together. As you ascend, the density drops off exponentially. At the top of Mount Everest, about 5.5 miles above sea level, the air is only about 1/3 as dense as at sea level, which is why climbers must use supplemental oxygen. At the edge of space, perhaps 60 miles up, the atmosphere is so thin it can barely be detected. This vertical structure matters for how light scatters. Most scattering happens in the lower, denser parts of the atmosphere, where molecules are abundant. The cumulative effect of all this scattering is what gives the sky its appearance, and understanding the details of how individual molecules scatter light is the key to understanding why that appearance is blue. The Dance of Molecules. Rayleigh Scattering Explained. The specific type of scattering that explains the blue sky is called Rayleigh scattering. Named after Lord Rayleigh, the British physicist John William Strutt, who worked out the mathematical theory of this phenomenon in the late 1800s. Rayleigh scattering describes what happens when light encounters particles much smaller than its wavelength, which is precisely the situation we have with visible light and air molecules. The theory Rayleigh developed makes a striking prediction. The amount of scattering is strongly dependent on the wavelength of light, varying inversely with the fourth power of wavelength. Let us unpack what this means. The intensity of scattered light is proportional to 1 divided by wavelength to the fourth power. This relationship, expressed mathematically as intensity proportional to 1 over lambda to the fourth, where lambda represents wavelength, has profound consequences. It means that light of short wavelength scatters much more strongly than light of long wavelength. It means that small changes in wavelength produce large changes in scattering. It means that the rainbow of colors in sunlight will not scatter equally, but that blue and violet light, with their short wavelengths, will scatter far more than red and orange light with their longer wavelengths. To make this concrete, consider red light with a wavelength of about 650 nanometers and blue light with a wavelength of about 450 nanometers. The ratio of these wavelengths is 650 divided by 450, which is approximately 1.44. But because scattering depends on the fourth power of wavelength, we must calculate 1.44 to the fourth power, which equals about 4.3. This means blue light scatters more than 4 times as strongly as red light. Violet light, with an even shorter wavelength around 400 nanometers, scatters even more strongly, roughly 9 times as much as red light. The physical mechanism underlying this wavelength dependence is subtle and beautiful. When a light wave encounters a molecule, the oscillating electromagnetic field of the wave exerts forces on the charged particles within the molecule, primarily the electrons. These electrons begin to oscillate at the same frequency as the incoming light. An oscillating charge is like a tiny antenna, radiating electromagnetic waves in various directions. The electrons in the molecule thus become sources of scattered light, re-emitting radiation that spreads outward from the molecule. The efficiency of this process, how strongly the molecule scatters light of a given wavelength, depends on the size of the oscillations induced in the electrons. Higher frequency light, which corresponds to shorter wavelength light since frequency and wavelength are inversely related, oscillates more rapidly. This more rapid oscillation drives the electrons in the molecule harder and faster, creating larger amplitude vibrations. These larger vibrations produce stronger re-radiated light, meaning more intense scattering. The fourth power dependence on wavelength emerges from the details of this interaction, from the mathematics of how oscillating charges radiate electromagnetic energy. Imagine now a beam of white sunlight striking a region of atmosphere. The beam contains all colors of visible light mixed together in roughly equal proportions. As this light encounters nitrogen and oxygen molecules, scattering begins. The blue and violet components scatter much more strongly than the red and orange components. These scattered blue and violet photons head off in new directions, spreading throughout the sky. They may scatter again, off other molecules, and again gradually diffusing through the atmosphere. Meanwhile, the longer wavelength red and orange light continues largely in its original direction, scattering much less frequently, traveling through the atmosphere with less deflection. The result is that when you look at any part of the sky away from the sun, you see light that has been scattered by air molecules. This scattered light is enriched in blue wavelengths because blue scatters so much more effectively than other colors. The sky appears blue not because there is something intrinsically blue about air, but because air selectively scatters blue light from the sun's white spectrum, sending that blue light toward your eyes from all directions across the celestial dome. The blue you see is sunlight, white light from the sun, sorted by the scattering process into its component colors, with blue dominating the scattered light that reaches you from the sky. This scattering happens in all directions, not just toward the ground. Blue light scatters upward as well as downward, sideways as well as vertical. The atmosphere becomes filled with this scattered blue light, glowing softly with the color that gives our sky its characteristic hue. If you were to look at Earth from space, you would see this blue glow surrounding the planet, a luminous halo created by scattered sunlight, the same phenomenon that makes the sky blue from the ground, creating a visible aura around the world when viewed from above. Rayleigh scattering is not unique to Earth's atmosphere. It occurs anywhere light passes through a medium containing particles much smaller than the wavelength of the light. It happens in gases, in liquids, even in some transparent solids. It occurs in optical fibers, where microscopic density variations in the glass scatter light, limiting how far signals can travel before they become too weak to detect. It occurs in space itself, where interstellar dust scatters starlight, making distant stars appear redder than they truly are, because blue light is scattered away more effectively. Rayleigh scattering is a fundamental phenomenon of nature, a consequence of how light and matter interact, and the blue sky is perhaps its most visible and beautiful manifestation. Why blue and not violet? If Rayleigh scattering favors short wavelengths so strongly, and violet light has an even shorter wavelength than blue light, why is the sky not violet? This is an excellent question, one that highlights the fact that the color of the sky depends not just on physics, but also on biology, on the way human eyes and brains process light. The answer involves several factors working together, each contributing to the final perception of a blue rather than violet sky. First, consider the nature of sunlight itself. While it is often said that the sun produces white light containing all colors equally, this is not quite accurate. The sun is not a perfect black body radiator at a single temperature. It has a complex spectrum shaped by the nuclear reactions in its core and the absorption and emission processes in its outer layers. The spectrum of sunlight at the top of Earth's atmosphere peaks in the green part of the spectrum, but extends across all visible wavelengths. Critically, however, the sun produces significantly less violet and deep blue light than it does light in the middle of the visible spectrum. When you look at the actual spectrum of sunlight, the amount of energy at 400 nanometers in the violet is considerably less than the amount at 450 or 500 nanometers in the blue and green. So, while violet light scatters more strongly per photon than blue light, there are fewer violet photons to begin with. The strong scattering of violet light competes with its lower abundance in the solar spectrum, partially offsetting what would otherwise be a violet-dominated sky. Second, the atmosphere itself absorbs some light, particularly at shorter wavelengths. Ozone in the stratosphere absorbs strongly in the ultraviolet, and continues to absorb somewhat into the violet part of the spectrum. Other atmospheric constituents also contribute to absorption. This means that as sunlight travels through the atmosphere, some of the violet light is removed not by scattering, but by absorption, converted into heat rather than re-emitted as scattered light. This preferential absorption of violet further reduces the violet component reaching the lower atmosphere where we observe the sky. Third, and perhaps most importantly, human eyes are not equally sensitive to all wavelengths of light. Our color vision depends on 3 types of cone cells in the retina, each most sensitive to a different range of wavelengths. One type, often called S-cones, responds most strongly to short wavelengths in the blue-violet range. Another type, M-cones, responds to medium wavelengths in the green-yellow range. The third type, L-cones, responds to longer wavelengths in the yellow-orange-red range. The brain constructs our perception of a color from the relative responses of these 3 cone types. Critically, the S-cones that respond to short wavelengths have a sensitivity that peaks around 440 nanometers, in the blue rather than the violet. The response falls off at shorter wavelengths, meaning we are less sensitive to violet than to blue. Additionally, there are far fewer S-cones than the other cone types, roughly only 5 to 10% of all cones, compared to the much more numerous M-cones and L-cones. This means our eyes are simply not as good at detecting violet light as they are at detecting blue light. When blue and violet light mix together, as they do in the scattered light from the sky, our visual system does not register them as separate colors in the way a spectrometer would. Instead, the brain integrates the signals from all 3 cone types to create a single perception of color. The relatively weak violet signal from the sparse S-cones at their tail of sensitivity combines with a stronger blue signal from S-cones at their peak, and some contribution from M-cones that also respond to shorter blue wavelengths. The result is a perception that integrates across this range and appears to us as blue rather than violet. There is also a fourth factor, which involves the scattering process itself. While Rayleigh scattering predicts the intensity of scattered light at each wavelength, it also predicts the angular distribution of that scattered light. Light scatters preferentially in forward and backward directions rather than at 90 degrees. However, multiple scattering events, which occur as light bounces from molecule to molecule, tend to randomize the direction of scattered light. The blue wavelengths, scattering more frequently, undergo more scattering events on average before reaching your eye. This multiple scattering tends to make the scattered light more diffuse and uniform across the sky, contributing to the overall appearance. When all these factors combine, the lower intensity of violet in sunlight, the absorption of violet in the atmosphere, the reduced sensitivity of human eyes to violet wavelengths, and the way our brain processes color signals, the result is that we perceive the sky as blue rather than violet. On a hypothetical planet with a star that produced more violet light, with an atmosphere that did not absorb violet, and viewed by eyes more sensitive to short wavelengths, the sky might indeed appear violet or purple. But on Earth, with our particular sun, our particular atmosphere, and our particular biology, the sky appears the color we call blue. This reminds us that color is not a pure property of light itself, but an interpretation created by the interaction between physical wavelengths and biological perception. The same sky might appear somewhat different to animals with different vision. Birds, which have 4 types of color-sensitive cones, including one sensitive to ultraviolet light, perceive the sky in colors we cannot even imagine. The sky they see includes information from ultraviolet wavelengths that scatter even more strongly than violet, adding dimensions to their perception that are entirely invisible to us. The blue sky we see is the human version of a phenomenon that exists independently of us, but that we can only know through the particular filters of our evolved sensory systems. The journey through different times of day. The color of the sky is not constant. It shifts throughout the day, transforming from the pale blue of dawn to the deep azure of midday to the spectacular reds and oranges of sunset and back to darkness. These changes arise from the same physics that creates the blue sky in the first place, but modified by the changing path length of sunlight through the atmosphere as the sun moves across the sky. Understanding this daily cycle deepens our appreciation of how thoroughly the atmosphere transforms the light we receive from the sun. At noon, when the sun is directly overhead, sunlight takes the shortest possible path through the atmosphere to reach the ground. It enters at the top of the atmosphere and travels roughly straight down, passing through perhaps 10 miles of air, depending on your location and elevation. This is the minimum path length, the least amount of air sunlight must traverse. Under these conditions, scattering occurs, but the effect is moderate. Blue light scatters more than red, creating the blue sky, but there is still plenty of light of all wavelengths reaching the ground directly from the sun. The sun appears white or slightly yellowish, and the sky is a clear, brilliant blue. As the sun moves toward the horizon, either in the morning as it rises or in the evening as it sets, the geometry changes dramatically. When the sun is near the horizon, sunlight must travel through much more atmosphere to reach you. It enters the atmosphere at an angle, slanting through layer after layer of air. The path length can become 30, 40, even 50 times longer than when the sun is overhead. This extended journey through the atmosphere has profound effects on both the appearance of the sun itself and the color of the sky. Consider what happens to sunlight on this longer path. As the light travels through mile after mile of air, it undergoes scattering again and again. Each molecule it encounters has a chance to scatter it, and over a long path, almost all of the blue and violet light will be scattered away from the direct beam. This is sometimes called bulk attenuation. The direct beam of sunlight becomes progressively more depleted of short wavelengths as it travels through increasing amounts of air. By the time it reaches the lower atmosphere where you stand, almost all the blue and violet has been scattered out, leaving predominantly red, orange, and yellow light in the direct beam. This is why the sun itself appears reddish at sunrise and sunset. You are looking directly at the sun, seeing the light that has survived the long journey through the atmosphere without being scattered away. That light is enriched in long wavelengths because the short wavelength scattered away long ago. The sun, which appeared white or yellow at noon, now glows orange, red, or even deep crimson, its color shifted dramatically by the cumulative effect of scattering across a long atmospheric path. Meanwhile, the light that was scattered away, all those blue and violet photons that bounced off molecules along the way, has spread throughout the atmosphere. Some of it scattered back out to space, lost to the planetary system. But much of it scattered into the sky around you, contributing to the light you see when you look away from the sun. At sunset, when you look toward the sun, you see the depleted, reddened direct beam. When you look away from the sun, overhead or toward the opposite horizon, you still see scattered blue light, though it may be tinged with other colors from the complex interplay of multiple scattering, and the reddened light from the setting sun reflecting off the clouds or particles in the air. The sky directly around the setting sun often takes on spectacular colors: oranges, pinks, reds, purples. These arise from several effects. The reddened sunlight illuminates clouds and particles in the atmosphere, which reflect or scatter that colored light toward you. Light scatters multiple times, mixing red from the direct beam with blue from scattered light, creating intermediate hues. The geometry of your viewing angle, the specific particles in the air, the moisture content, all these factors influence the precise colors you see. No two sunsets are identical because the atmospheric conditions are never exactly repeated. There is a period called the blue hour, occurring twice daily, once before sunrise and once after sunset, when the sun is below the horizon but the sky is still illuminated. During the blue hour, direct sunlight is blocked by the curve of the earth, but the atmosphere high above you is still in sunlight. Light from the sun, now below your horizon, illuminates the upper atmosphere, scattering through the air above you and creating a soft, diffuse blue glow. This light has traveled an even longer path through the atmosphere than sunset light. But because you are seeing scattered light rather than the direct beam, and because the scattering is happening in the upper atmosphere where the air is cleaner and less filled with particles, the blue color can be particularly pure and beautiful. As the sun continues to descend below the horizon, the illuminated portion of the atmosphere shrinks. The scattered light grows dimmer, and eventually twilight fades into night. The process reverses at dawn. First, the sky begins to brighten with that soft blue glow as the upper atmosphere catches the light of the sun still below your horizon. Then the sun approaches the horizon, and the sky near it begins to show the reds and oranges of sunrise. Finally, the sun breaks above the horizon, and as it climbs, the sky transitions through the morning colors back to the brilliant blue of midday. This daily cycle is one of the most reliable natural phenomena, repeated every day everywhere on Earth where the sky is clear enough to see. It is driven by the rotation of our planet, by the spherical geometry that changes the angle between sunlight and the surface throughout the day, and by the physics of light scattering in an atmosphere. Our ancestors watched these color changes throughout human history, using them to mark time, to navigate, to predict weather. They wove the colors of dawn and dusk into poetry and myth, saw omens in unusual hues, celebrated the beauty without knowing its cause. Now we understand the mechanism, yet the beauty remains undiminished, perhaps even enhanced by knowing that these colors arise from something as simple and profound as light, bouncing off molecules of air, sunset, symphony, when the sky turns fire. Sunsets hold a special place in human experience. Across cultures and throughout history, people have gathered to watch the sun descend, painting the sky with colors that seem impossible, as if the heavens themselves are on fire. There is something primal in our response to sunset, something that draws us to pause and witness this daily transformation. Understanding the physics behind these spectacular displays does not diminish their emotional impact. If anything, it deepens our appreciation, revealing the intricate choreography of light and atmosphere that creates beauty through simple, universal principles. The most dramatic sunsets occur when the atmosphere contains more particles than usual. Though the relationship between particles and the sunset color is more complex than often assumed. When the sky is very clean and clear, sunsets can be beautiful but relatively pale, showing soft yellows and oranges. The most vivid and intense sunsets often happen when there are aerosols in the atmosphere, tiny particles suspended in the air that modify how light scatters. However, the type and size of particles matters enormously, and not all particles enhance sunset colors. Some can actually diminish them. Volcanic eruptions provide some of the most spectacular sunsets ever witnessed. When a volcano erupts explosively, it can inject massive amounts of material into the stratosphere, the layer of atmosphere above the troposphere where weather occurs. Sulfur dioxide gas from the volcano reacts with water in the stratosphere to form tiny droplets of sulfuric acid, creating an aerosol layer that can persist for months or even years. These droplets are small enough that they scatter light effectively, but large enough that they scatter all wavelengths somewhat equally, not just blue. The result is that they enhance the scattering and spreading of the already reddened sunset light, creating unusually vivid and extensive displays of orange and red. The eruption of Mount Tambora in 1815 created aerosol veils that persisted for years, leading to unusually colored sunsets observed around the world. Some historians believe these unusual atmospheric effects influenced the paintings of the artist J.M.W. Turner, who created works with intensely colored, dramatic skies during this period. Similarly, the eruption of Krakatoa in 1883 produced spectacular optical phenomena, including unusually bright twilights and vivid sunset colors observed globally. More recently, the 1991 eruption of Mount Pinatubo in the Philippines created a stratospheric aerosol layer that intensified sunsets worldwide for several years. Dust storms and wildfires can also affect sunset colors, though usually with different results than volcanic aerosols. Dust particles and smoke particles tend to be larger and more irregular than volcanic aerosols. When these particles are present in large quantities, they can scatter light less selectively, removing color from sunsets and creating hazy, washed-out skies. However, smoke particles from wildfires sometimes create intensely red sunsets and even blood-red suns, as the large particles preferentially remove blue and green from sunlight, leaving only red. These are often eerie rather than beautiful, tinged with the knowledge of the fires that produced them. The type of clouds present also dramatically affects sunset appearance. High clouds, particularly cirrus and altocumulus, are ideal for spectacular sunsets. These clouds exist above most of the atmosphere's water vapor and pollution, intercepting sunlight that has already been reddened by its long atmospheric path, but has not yet been diluted or scattered by lower-level haze. When this reddened light strikes high clouds, they reflect and scatter it, sometimes creating brilliant displays of scarlet, orange, and pink. The three-dimensional structure of clouds adds texture and variation, with some parts in direct sun showing vibrant colors while shadows create contrasts of a deep purple or blue. Low clouds, such as stratus or stratocumulus, rarely produce dramatic sunset colors. These clouds exist in the lower troposphere, within the boundary layer where pollution and moisture are concentrated. Sunlight reaching them has already passed through the dirty lower atmosphere, becoming attenuated and less intensely colored. Moreover, low clouds often block the view of higher atmospheric features that might otherwise contribute to the sunset's color. However, exceptions occur when the lower atmosphere is unusually clean, such as over tropical oceans or in polar air masses, allowing even low clouds to display vivid sunset hues. There is a saying that has persisted for centuries. Red sky at night, sailor's delight. Red sky at morning, sailor, take warning. This bit of weather folklore has a basis in atmospheric physics. In mid-latitude regions where weather generally moves from west to east, a red sunset suggests that the atmosphere to the west is clear enough to allow the sun's light through to create those colors, implying that fair weather is approaching. A red sunrise suggests clear air to the east, where weather has already passed, but potentially stormy conditions to the west, where weather is coming from. While not infallible, this rule captures a real correlation between sky color and weather patterns. The angle at which you view the sunset also matters. When you look directly at the setting sun, you see the depleted, reddened direct beam, often appearing as a brilliant orange or red disk. When you look at the sky above or to the sides of the setting sun, you see a mixture of scattered light, some from the reddened direct beam illuminating the atmosphere and particles, some from blue light still being scattered from sunlight reaching other parts of the sky. This creates gradients of color, transitions from orange near the sun through pink and purple higher up, sometimes to blue overhead if the sun is just beginning to set. These gradients shift and change as the sun descends, creating a dynamic display that can last for 30 minutes or more. Some of the most beautiful sunset colors appear in the opposite part of the sky from the setting sun. This is called the belt of Venus, a pink or reddish band that appears just above the horizon opposite the sunset, bounded above by a darker bluish band called Earth's shadow. The belt of Venus is created by backscattered light from the sunset, reddened sunlight that is scattered off the particles in the atmosphere and traveled across the sky to illuminate the air opposite the sun. The Earth's shadow is exactly what it sounds like, the shadow of the Earth itself cast onto the atmosphere. Visible because you are looking at air that is no longer in direct sunlight, illuminated only by scattered light from the sky above. Photography cannot quite capture the full experience of a great sunset. The human eye has a dynamic range that far exceeds cameras, able to see detail in both bright areas near the sun and darker areas further away simultaneously. Cameras must choose an exposure, either preserving the bright areas and leaving dark areas nearly black, or exposing for the darker areas and blowing out the highlights. Moreover, cameras capture color differently than eyes, with different spectral sensitivities and different processing. Yet sunset photography remains endlessly popular, as people attempt to preserve even an imperfect record of these fleeting moments when the sky transforms into something that seems almost unreal in its beauty. The role of particles and pollution. While Rayleigh scattering by molecules dominates the color of a clear blue sky, particles in the atmosphere play a complex and important role in modifying sky color. The term aerosol in atmospheric science refers to any tiny particle or droplet suspended in air. Aerosols come from many sources. Sea spray creates salt particles. Dust storms loft soil into the air. Volcanic eruptions inject ash and sulfate particles. Plants release organic compounds that form particles, and human activities contribute smoke, soot, and pollution. These particles span a huge range of sizes, from a few nanometers to hundreds of micrometers, and their effects on light depend critically on their size, composition, and concentration. When particles are very small, much smaller than the wavelength of light, they scatter light through Rayleigh scattering just like molecules do. They contribute to the blue color of the sky, adding to the effect of nitrogen and oxygen molecules. However, most aerosol particles are larger than this, with sizes comparable to or larger than visible wavelengths. These particles scatter light through a different mechanism called Mie scattering. Named after the German physicist Gustav Mie, who developed the theory in 1908. Mie scattering is more complex than Rayleigh scattering. The amount of scattering still depends on wavelength, but the dependence is much weaker than the fourth power relationship of Rayleigh scattering. For particles comparable to the wavelength of light, scattering is strong for all visible wavelengths, not just for blue. This means that when large particles are present, they scatter light of all colors roughly equally. The result is that sky illuminated by light scattered from large particles appears white or gray rather than blue. This is why hazy skies, filled with pollution or dust, often appear pale or washed out. The blue is still there from molecular Rayleigh scattering, but it is diluted by white light from particle scattering. Clouds are an extreme example of MI scattering. Cloud droplets are typically 10 to 20 micrometers in diameter, much larger than visible wavelengths. They scatter all colors of light very efficiently and roughly equally. Sunlight scattered by cloud droplets emerges white, which is why clouds appear white when illuminated. The same principle applies to fog, which is essentially a cloud at ground level, and to the white appearance of snow, which consists of ice crystals that scatter all wavelengths equally. When particles are this large, wavelength-dependent scattering is negligible, and the color of scattered light matches the color of the incident light. The concentration of particles also matters enormously. On a day with pristine, clean air, molecular scattering dominates, and the sky is a deep, saturated blue. As particle concentration increases, whether from natural sources or pollution, more and more of the skylight comes from particle scattering rather than molecular scattering. The sky becomes progressively paler, transitioning from deep blue to light blue to pale blue-white to gray. In heavily polluted cities, the sky can appear nearly white even on sunny days, the blue entirely washed out by the overwhelming contribution of light scattered from pollution particles. Not all particles scatter light equally. The scattering efficiency depends on the ratio of particle size to wavelength, on the shape of the particle, and on its refractive index, the measure of how much it bends light. Spherical particles of uniform size can sometimes create unusual color effects. For example, pollen grains or certain types of dust, if present in large quantities and of uniform size, can create blue moons or blue suns, strange phenomena where the moon or sun takes on a distinctly blue tint. This happens when the particles are just the right size to scatter red light more effectively than blue light, the opposite of what usually occurs. These events are rare and striking when they happen, a reminder that the interaction of light and particles can produce surprises. Smoke from wildfires deserves special mention. Wildfire smoke contains particles of many sizes, from large ash particles to tiny molecules and nanoclusters from incomplete combustion. Fresh smoke near a fire often contains many large particles that scatter all wavelengths equally, creating a white or gray smoke plume. However, as smoke ages and disperses, the larger particles settle out, leaving smaller particles suspended in the air. These smaller smoke particles, combined with gases from the fire, can create intensely colored skies. During major wildfires, sunsets can become abnormally red, and even at midday, the sun can appear orange or red as blue light is scattered away. People hundreds or even thousands of miles downwind from major fires can observe these effects when smoke spreads across regions. There is an important distinction to make about pollution and sunset colors. While it is sometimes said that pollution makes sunsets more colorful, this is not always true and can be misleading. Heavy pollution from sources like urban smog tends to make sunsets paler and less vibrant, not more colorful. The large particles and droplets in heavy smog scatter all wavelengths equally, creating milky, washed-out skies. However, certain types of particles at certain concentrations can enhance sunset colors, particularly if they are small and occur in the middle or upper atmosphere, rather than in the dirty lower boundary layer. The relationship is complex and depends on the specific composition and distribution of particles. Volcanic aerosols, as mentioned earlier, can enhance sunsets because they consist of sulfuric acid droplets that are small, uniform in size, and located in the stratosphere above weather and pollution. These conditions are ideal for creating vivid colors. But the black carbon particles from diesel exhaust or the mixture of particles in urban pollution generally degrade rather than enhance sky color. The most spectacular sunsets typically occur when the lower atmosphere is clean and clear, allowing reddened sunlight to reach high clouds or upper atmospheric particles that can then scatter it to create vivid colors. Scientists monitor atmospheric aerosols carefully for multiple reasons. Aerosols affect climate by scattering and absorbing sunlight, changing the energy balance of the atmosphere. They serve as seeds for cloud droplets, affecting cloud formation and precipitation. They impact air quality and human health, particularly fine particles that can penetrate deep into lungs, and they modify the color and appearance of the sky, affecting visibility and the beauty of atmospheric phenomena. Networks of instruments around the world measure aerosol concentration, size, distribution, and optical properties, providing data that helps us understand both the practical impacts of aerosols and their role in creating the beautiful and varied appearances of the sky we observe day by day. Other worlds, other skies. The blue sky of Earth is not universal. It arises from the specific combination of our sun's spectrum, our atmosphere's composition, and the particular physics of Rayleigh scattering. On other worlds, with different suns and different atmospheres, skies take on different colors, offering a profound reminder that the blue we take for granted is a consequence of particular circumstances. Beautiful, but not inevitable. Exploring these alien skies deepens our understanding of our own and reveals the diversity of atmospheres that can exist throughout the universe. Mars, our neighboring planet, has a sky that appears reddish or butterscotch-colored, a striking contrast to Earth's blue. This difference arises from multiple factors. First, Mars has a much thinner atmosphere than Earth, less than 1% as dense. The scattering by air molecules is correspondingly much weaker. There is some Rayleigh scattering, which would tend to create a faint blue color, but the effect is subtle because there are so few molecules. What dominates the appearance of the Martian sky is not molecular scattering, but scattering by dust. Mars is a dusty world. Fine particles of iron-rich dust are suspended in the Martian atmosphere more or less permanently, lofted by winds and dust storms and settling very slowly in the thin air. These dust particles are large compared to the wavelength of light, so they scatter all colors roughly equally through Mia scattering, creating a reddish or yellowish cast. The dust itself is reddish due to iron oxides, essentially rust, and this color imparts itself to the scattered light. Additionally, the red dust on the surface reflects red light upward, and this ground-reflected light combines with skylight to give the Martian sky its characteristic color. When dust storms occur, the Martian sky becomes even more deeply red or pink, with the increased dust concentration overwhelming any other effects. Interestingly, observations from Mars landers and rovers have revealed that the Martian sky shows blue near the Sun. Around the solar disk, where you are looking at light that has scattered only a little, Rayleigh scattering by the thin Martian atmosphere becomes visible, creating a blue glow immediately around the Sun, even while the rest of the sky is red or yellow. This creates a strange inverted effect compared to Earth, where the sky is blue except near the Sun, which appears yellow or white. On Mars, the sky is red except near the Sun, which appears blue. This is a beautiful demonstration of how the balance between molecular scattering and particle scattering determines sky color. Venus has an atmosphere very different from Earth's, composed primarily of carbon dioxide with thick clouds of sulfuric acid droplets. The Venusian atmosphere is so thick and cloudy that the surface is perpetually shrouded, receiving only diffuse, scattered light rather than direct sunlight. If you could stand on the surface of Venus, which would be challenging given the extreme temperatures and pressures, the sky would appear yellowish or orange. This color comes from the absorption and scattering properties of the sulfuric acid clouds and the carbon dioxide atmosphere, which filter and redden, the sunlight penetrating down to the surface. The intensity would be surprisingly high, similar to an overcast day on Earth, but the color would be distinctly warm, creating an alien landscape where everything is bathed in golden orange light. Giant planets like Jupiter and Saturn have thick atmospheres composed mainly of hydrogen and helium, with traces of methane, ammonia, and other compounds. If you could somehow descend into these atmospheres and look up, which is a thought experiment since these planets have no solid surface to stand on, the sky would likely appear blue, though the exact shade would depend on depth and the presence of clouds and hazes. Molecular scattering of sunlight by hydrogen and helium molecules would create a Rayleigh scattering effect similar to Earth's. However, as you descended deeper, the sky might transition to other colors as pressure and temperature changed the atmospheric properties, and as you approached cloud layers of different compositions. Titan, the largest moon of Saturn, has a thick atmosphere composed primarily of nitrogen, similar to Earth, but also containing significant methane. The Titanian sky appears orange due to a thick haze of organic compounds high in the atmosphere. These complex organic molecules, formed by photochemistry driven by sunlight and energetic particles, create a smog layer that absorbs blue light strongly, allowing red and orange to penetrate. The surface of Titan receives a dim, reddish light, and the sky would appear orange or brown, a twilight world despite the sun being in the sky. This demonstrates how atmospheric chemistry can dramatically alter sky color through absorption rather than just scattering. Exoplanets orbiting other stars would have even more diverse skies. A planet orbiting a red dwarf star, receiving light that is already shifted toward longer wavelengths, might have a sky that appears red or purple, depending on its atmospheric composition. A planet with an atmosphere rich in exotic gases or with different pressure and temperature profiles might scatter light in ways that create colors we can barely imagine. As our ability to study exoplanet atmospheres improves through techniques like transmission spectroscopy, where we observe starlight filtering through an exoplanet's atmosphere, we may begin to map the colors of alien skies, adding to the growing library of worlds beyond our own. Understanding why Earth's sky is blue provides a framework for predicting what skies should look like elsewhere. The principles of light scattering are universal. Rayleigh scattering will occur wherever light passes through molecules much smaller than its wavelength. Mie scattering will occur wherever larger particles are present. Absorption will modify colors wherever molecules or particles can absorb particular wavelengths. By knowing the composition, density, and structure of an atmosphere, along with the spectrum of the star illuminating it, we can predict sky color with reasonable confidence. This is how atmospheric scientists analyze data from spacecraft and telescopes, reconstructing the appearance of worlds we may never visit but can nonetheless visualize through the lens of physics. The blue sky of Earth, seen from this perspective, is both ordinary and special. Ordinary because it follows universal physical principles that apply anywhere. Special because the particular combination of a sun like ours and an atmosphere like ours produces a color that is distinctly ours. A blue that humans have looked up at throughout our entire existence as a species. A blue that has shaped our psychology, our language, our art. It is simultaneously a physical phenomenon and a human experience, a scientific fact, and a source of endless wonder. The human connection. How we perceive color. The blue sky exists as a physical phenomenon independent of any observer. Light of particular wavelength scattered by atmospheric molecules according to mathematical principles. Yet the experience of blue, the perception of that color as blue rather than some other hue, is a creation of human biology and psychology. Understanding how we perceive color adds another layer to our appreciation of the sky, revealing that what seems like a simple, direct observation is actually a complex process of light detection, neural processing, and mental construction. Color vision begins in the retina, the light-sensitive layer at the back of the eye. The retina contains two main types of photoreceptor cells: rods, which are very sensitive to light but do not distinguish colors, and cones, which are less sensitive but provide color vision. Humans have three types of cone cells, each containing a different light-sensitive pigment that responds most strongly to a different range of wavelengths. These are traditionally called S cones, M cones, and L cones for short, medium, and long wavelengths. S cones respond most strongly to light with wavelengths around 420 to 440 nanometers in the blue-violet part of the spectrum. M cones peak around 530 to 540 nanometers in the green-yellow range. L cones peak around 560 to 580 nanometers in the yellow-orange range. Despite their names, none of these cones responds exclusively to a single color. Each has a broad response curve, responding to a range of wavelengths with varying sensitivity. The response curves overlap, particularly the M cones and L cones, which have quite similar sensitivities. When light enters the eye and strikes the retina, each photon that is absorbed by a cone triggers a cascade of molecular events, eventually producing an electrical signal that travels along the optic nerve to the brain. The brain receives signals from all three cone types simultaneously. By comparing the relative strengths of these signals, the brain can determine the wavelength composition of the light entering the eye. If S cones respond strongly and M and L cones weakly, the brain interprets this as blue or violet. If M cones respond strongly, it might be green. If L cones respond most and M cones moderately, it might be yellow or orange. If all three respond strongly and equally, it might be white. This process of comparing signals across different cone types is called a opponent processing. In the retina and subsequent neural processing stages, signals are not transmitted as independent values, but as differences. One pathway compares L cone signals to M cone signals, essentially computing red minus green. Another compares S cone signals to the sum of L and M, computing blue minus yellow. A third pathway computes overall brightness. These three opponent channels form the basis of our color perception. The actual perception of color happens in the brain, in the visual cortex, where these opponent signals are integrated with information about spatial patterns, motion, and context. Color perception is not fixed, but can be influenced by surrounding colors, by expectations, by adaptation to ambient lighting, by memory, and by attention. The brain constantly interprets and adjusts color signals to maintain stable perception, despite changing illumination, a process called color constancy. This is why a white shirt looks white both in sunlight and in indoor lighting, even though the actual wavelengths reaching your eye are quite different in the two situations. The blue of the sky, when you perceive it, is the result of this elaborate process. Light scattered from the sky, enriched in short wavelengths by Rayleigh scattering, enters your eye and stimulates S cones primarily, with some response from M cones and little from L cones. The pattern of responses is transmitted to the brain as opponent signals, processed through multiple stages of visual processing, compared with signals from other parts of your visual field, integrated with your expectations and memories, and finally emerges as the conscious perception of blue. The entire process, from photon entering eye to conscious awareness of color, takes only a fraction of a second, yet involves millions of neurons and billions of synaptic connections. Different people perceive colors slightly differently. The precise wavelength sensitivities of cone pigments vary somewhat from person to person due to genetic differences. Some people have variants of the genes that encode cone pigments, shifting their sensitivity curves slightly. This means that two people looking at the same sky might have subtly different perceptions of its color. One seeing a blue that appears slightly more green-tinged, another seeing a blue with more violet. These differences are usually small, and most people would agree the sky is blue, but the subjective experience of that blue is unique to each individual. Some people have color vision deficiencies, often called color blindness, where one or more cone types is missing or non-functional. The most common form, affecting about 8% of males and much smaller percentage of females, involves the L or M cones, leading to difficulty distinguishing reds and greens. For these individuals, the blue sky still appears blue, since it is primarily detected by S cones, which are typically normal even when other cone types are affected. However, their perception of sunset colors, which involve mixtures of red, orange, and yellow that depend on M and L cone function, might be quite different from typical color vision. A small number of women may have 4 types of cone cells rather than 3, a condition called tetrachromacy. This could occur if a woman inherits 2 slightly different versions of the gene for L cones or M cones, one on each X chromosome, and both are expressed. Tetrachromats may perceive colors differently than trichromats, potentially distinguishing subtle color differences that others cannot see. Their perception of the sky might include nuances invisible to the rest of us, though since they have lived with this vision their entire lives and have learned color names from trichromats, it is difficult to know exactly how their experience differs. Animals perceive colors very differently than humans. Many mammals, including dogs and cats, have only 2 types of cones, seeing the world in a more limited palette roughly analogous to human red-green color blindness. Birds typically have 4 cone types, including one sensitive to ultraviolet light, giving them a richer color vision than ours. They can see patterns and contrasts in the sky that are invisible to us, particularly in the UV range, where scattering is even stronger than for visible blue. Insects, like bees, also see ultraviolet and perceive colors quite differently than we do. The blue sky we see is the human version of a phenomenon that every creature with vision interprets through its own biological filters. Understanding the biology of color perception completes the story of the blue sky. It is a physical phenomenon, light scattering by molecules according to principles that would operate even if no one was watching. But it is also a perceptual phenomenon, an experience created by the interaction of that physical light with biological sensors and neural processors that evolved over millions of years. The blue we see is both out there, a property of atmospheric scattering, and, in here, a construction of our visual system. This dual nature of color, simultaneously objective and subjective, physical and phenomenological, reminds us that our experience of the world is always a collaboration between external reality and internal interpretation, a partnership between universe and observer that creates the rich, colorful experience of consciousness. Closing reflections and call to action. As we come to the end of this journey through light and atmosphere, through physics and perception, through science and wonder, let yourself settle more deeply into rest. You have traveled with sunlight from its birth in the core of the sun, through 93 million miles of empty space, into the embrace of Earth's atmosphere, where molecules scattered it into the blue that stretches above us each day. You have understood the mathematics of scattering, the inverse fourth power relationship that favors short wavelengths, the reason why blue dominates while violet hides in the wings. You have witnessed how the changing angle of sunlight throughout the day transforms the sky from blue to red to blue again, painting each dawn and dusk with colors that have inspired humanity since consciousness first arose. The question of why the sky is blue turns out to be a doorway into deep understanding. It required humanity to develop the wave theory of light to discover that air is made of molecules, to formulate the mathematics of scattering, to understand how our eyes and brains create color perception. Answering this one simple question demanded insights from physics, chemistry, atmospheric science, biology, and psychology. It connected phenomena ranging from the quantum mechanics of how photons interact with electrons to the evolution of human vision. This is characteristic of the best scientific questions. They appear simple on the surface, but open into vast landscapes of interconnected knowledge once we begin exploring them seriously. Every clear day, the blue sky is there, waiting to be noticed, waiting to be wondered about, waiting to teach anyone who pauses to pay attention. It is a demonstration of physics accessible to everyone, a laboratory that exists above our heads, performing experiments in light scattering billions of times per second. No equipment is required to observe it, no technology needed to experience it. You need only look up and ask why. This accessibility makes the blue sky a perfect introduction to scientific thinking, a phenomenon that can lead from casual observation to deep understanding, from childish questioning to sophisticated comprehension. There is something profound about understanding why the sky is blue. It changes how you see the world. Where before there was simply blue, now there are photons bouncing off nitrogen and oxygen molecules. Where before there was color, now there is wavelength and scattering cross-section, and the fourth power of wavelength. The blue does not become less beautiful for being understood. If anything, it becomes more beautiful, layered with meaning, connected to a vast web of physical law that governs not just our sky, but the universe entire. The sunset becomes not just pretty colors, but a demonstration of how path length affects scattering, how particles modify light, how our star bathes our world in the full spectrum, and our atmosphere sorts that spectrum into the colors we see. This knowledge connects you to something larger. When you understand the blue sky, you hold within your mind principles that explain not just Earth's atmosphere, but atmospheres around other worlds, not just visible light, but all electromagnetic radiation. Not just this moment, but every moment since our planet's atmosphere formed billions of years ago. You become part of a chain of understanding that stretches from ancient wanderers through 19th century physicists to modern atmospheric scientists. You carry forward a tradition of curiosity and explanation that represents one of humanity's greatest achievements, the gradual construction of a coherent picture of how nature works. If you have enjoyed this peaceful exploration of light scattering and atmospheric color, I invite you to like this video and subscribe to the channel. Your support helps these sleepy scientific journeys reach others who might be curious, who might wonder, who might find comfort and fascination in understanding the world around them. Share this with someone who has ever looked up and asked why. Share it with a child who notices everything, who has not yet learned to stop questioning. Share it with anyone who finds peace in knowledge, who sleeps better knowing that the universe makes sense, that there are answers waiting for those who seek them. For now, as you drift towards sleep, let the image of the blue sky settle into your mind. Imagine yourself shrinking down until you can see individual molecules of nitrogen and oxygen floating in space, separated by distances vast from their perspective. Watch as a photon of light, a ripple in the electromagnetic field, approaches one of these molecules. See the photon's oscillating field-set electrons in the molecule vibrating. Watch as those vibrating electrons create their own electromagnetic waves, scattering light outward in all directions. See this process repeated trillions upon trillions of times throughout the atmosphere, creating that soft blue glow we call the sky. Feel yourself rising back up, growing larger until you stand once more at human scale, looking up at the blue dome overhead. But now you see it differently. You see the photons from the sun, their journey through space and air, their scattering and rescattering, their eventual arrival at your eye. You see the physics underlying the beauty, the mathematics beneath the color, the mechanism behind the wonder. And somehow, impossibly, the sky seems even more magnificent for being understood. The universe speaks in the language of mathematics and physics, but it creates poetry. The blue sky is both equation and experience, both calculation and contemplation, both scientific fact and source of endless beauty. You carry this knowledge now. Tomorrow, when you step outside and look up at the blue expanse, you will know why. You will understand the story that light and atmosphere tell together. And in that understanding, you will find a deeper connection to the world that has always been your home. Rest now. Let your breathing slow. Let your thoughts quiet. Let the blue sky fade into the darkness behind your closed eyes. You have learned something profound tonight, added another thread to your understanding of how reality works. Sleep well in the knowledge that the world makes sense, that questions have answers, that the beautiful blue stretching overhead each clear day arises from simple principles operating at scales beyond seeing to create effects magnificent enough to inspire endless wonder. Good night.